Right, so back again with another session. So so what I was saying is are you able to get me? Are you able to see the screen? Ça va?
Yes, sir. Can you just start afresh and start at the back?
Okay. So we have a particle that is moving in this trajectory like this one. Okay, we have a particle that is moving in this trajectory. So let's say a point M, a point moves from this point. A point moves from its position at M prime. It moves to a new position. Let's say M, like so. Well, the distance that it travels from M to M prime is known as S. Now S is known as l'abscisse curviligne. L'abscisse curviligne is the distance that this is going to travel. Actually, here we can even say ds, because it's une distance élémentaire. We can talk about the distance élémentaire. If we talk about distance élémentaire, we'll put ds there. So this is what we have here. So from M prime to S, like so. This is what we have. Then I said, if you consider a point that is here, let's say M prime prime, you also consider a point that is here. Let's say M prime prime prime. You consider a point that is also here. You say M prime 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 prime, like so. So at this particular point here, now let me just move my point M. Let me put it somewhere here. So here you can actually draw a circle here. You see that it's possible to draw a circle here with some origin at O here. And then the distance from the point M to the origin is known as ρ. This distance ρ is known as le rayon de courbure. So this is what I've written here. Rayon de courbure is the radius of this circle that we have here. So ρ, the distance from the point M to O, like so, is known as ρ, which is known as le rayon de courbure. So here, if I draw the tangent to this circle at the point M, then this tangent is what is going to carry this vector t. The unit vector t is going to be carried by the tangent. This is the t we are seeing here. And then the n we are seeing here is a vector that is perpendicular to this t that we are seeing here. So the n is a vector that is carried by this line that I've drawn here. So this is known as the normal vector. So it is going to be carried by what? It is going to be carried by a line that is perpendicular to the tangent. Same. You see that if I draw draw a circle here, and then this is my origin, like so, then this is going to be, so if I draw a tangent at this point, this is what is going to, this is the t that I have here. And then this is the normal vector that I have here. So you can see that the directions have changed. So same, if I draw it here, it will be different. That is why, for this reason, la base de série Frenet is known as une base locale. C'est une base locale. C'est une base locale. Then the first thing that you have to indicate on this trajectory before you even do anything, is le sens de mouvement. So the particle is moving from this end and going to this end. C'est très très important to indicate le sens de mouvement. Okay, le sens de mouvement, c'est très très important to indicate le sens de mouvement. So that is why the tangent, the arrow is also pointing in the direction of le sens de mouvement. Okay, so t is carried by this tangent. T is carried by the tangent. Then the normal is carried by the perpendicular line, a line that is perpendicular to the tangent. So then we've explained what t is. We've explained what n is. Now b is the vector product of t and n. So t vectorial n is going to be the vector product. Now, because we want to make sure that we cover as much as possible, I won't derive these expressions. So what I'll do is, in the next I'll create a small video where I explain where these formulas for n and t are coming from. I'll explain where these formulas for n and t are coming from. I'll make a small video to explain these formulas. However, just know for now that the normal vector has this expression. This is the expression of the normal vector, and then this is the expression of the tangent vector. So here the normal is going to be equal to ρ multiplied by the derivative of the vector t with respect to s. And then just also remember this formula. T is going to be equal to the distance of the vector OM with respect to S. Voilà, c'est ça. Just remember these two formulas. If you remember these two formulas for N and for T, you'll be warm and dry. So with everything that I've said, add this formula. I'll explain why the expression is like this in a small video that I'll make after this particular session. I'll explain why we have this formula for N and why we have this formula for T. For now, just remember these expressions, okay? Let's save a little bit of time, okay? Because that is what is important to remember. Now, you know how to calculate B, you know the expression for T, you know the expression for N. Now, as we are talking about any bars, it is important to know how to calculate the velocity in that particular basis. It is also important to know how to calculate the acceleration. Now, another thing that I want you to remember is that the vector of vitesse of the point M the unit vector is going to be this same vector T, because the velocity as well is along the tangent. So just like the vector T, velocity has a component along this direction. It does not have a component along the normal direction. So velocity has a component along this direction T, meaning the unit vector that we're going to use to represent the direction of the vector of vitesse is this vector T, the one that is carried by the tangent. So this vector T has the same direction as the vector of vitesse. This is what you're supposed to remember. The vector of vitesse has the same direction as this vector T that we are seeing here. Now, because velocity is a vector, it has direction and magnitude. So I cannot just say, okay, I cannot just write V is equal to the vector T. That is not going to be correct, because the vector T indicates the direction. Okay, so this velocity is a vector, and then it has a direction and a magnitude. This is the magnitude of the vector that I've represented here. This is the magnitude of the vector. And then to simplify things here, I've paused. Let this complicated thing, which means la norme de V, so which means the modulus of this vector, I've just said let the modulus be equal to this small v, such that the formula looks a little bit nice. So this is why I've written this. So up to this point, is everything alright? Is it clear up to this particular point? Is everything okay up to this point? Are we still having problems? Are we still having challenges? Is everything okay up to this point? The expression for the vector N, the expression for the vector T, how to calculate B, and the fact that velocity has the same direction as the vector T. That is why the unit vector in this case we're using to indicate the direction of the vector of vitesse is going to be along T. C'est clair? C'est clair? So that is why velocity has that expression, that is Vm is equal to V along the direction T. So is it okay? We make progress? Brian, is it clear? Okay. Bien. Okay. So this is what we have here. So this is what we have. So apart from this, remember I told you this expression. This is by definition. This expression I have here is by definition. I said, if you remember what I said when we were talking about here, I said that this expression for velocity, I've also written it here. It is true for any coordinate system. The expression for velocity, it is true for any coordinate system. The derivative of OM with respect to time is true for any coordinate system. That is why here we'll try to bring it in. We'll try to introduce this expression here. Because it is true for any coordinate system. Okay. Now, if you compare this expression with the expression that we've written on top, if you compare this expression with this expression that I've written on top, okay, what are the similarities? Okay, let's see. So here I have Vm is going to be equal to dOm, like so dt. Okay, I'll leave this the way it is. Now, the other one is like this. The other one is Vm is actually the magnitude, and then along this direction. So let me first of all write the full thing here. I know that V is that. Then what is the expression for T? The expression for T is here. It is dOm ds. That is the expression for T. It is dOm it is the OM ds. So here I have, if I compare these two, I can deduce the formula for how to calculate the magnitude. So now this is the OM ds. So if I write this one that is on the left like this, if I write it like this, if I say it is the OM, it is the OM divided by ds, and then ds divided by dt. Like so, I've not changed anything. Here you can simplify and then you get back to the original thing. I can write what is here. This I can write it as what follows here. Okay, this I can write it as what follows here. So if you look at this expression now, if you pay attention, if you pay particular attention, if you look at this expression and this expression, you see that this quantity here is the same quantity that is here. It simply means that because these two expressions, these two equations describe the same thing, it simply means that by identification, the magnitude is going to be given by ds divided by dt. Is it clear? If you compare these two expressions, you see that the magnitude is going to be given by ds divided by dt. C'est clair? You understand? The magnitude is given by ds divided by dt. By identification. So this, we get this one by identification. Huh? C'est bon?
Now kindly repeat
Okay.
on velocity.
So what I'm saying is this. I have two expressions for velocity. One coming from la base de Frenet. Then the other one is coming by definition of what velocity is. The other one is coming by the definition of what velocity is. Let's look at this expression that we are getting from la base de série Frenet. Let's develop it a little bit further. So how do we develop it a little further? We have Vm is equal to, now here we have V. Then what is the expression for this vector t? It is dOm, like so, divided by ds. This is the expression for the Vm. Okay, I end here for this one. But let's look at this one. How can I expand this one? So I want to compare these two formulas. So what I'm going to do is that I will say Vm like so, and then I'll differentiate this one. I'll differentiate this one. I'll try to introduce this item here. I'll try to introduce ds here. So I'll say dOm ds. Remember when we were differentiating ER, euro and phi with respect to t, we had to use phi to come up with that differentiation. So here we are doing the same. We want to introduce this ds here. So I'll say dOm ds, and then I'll say ds and then dt, like so. Now if you compare these two formulas, if you write this formula side by side, now let me just write them side by side. Let me write the other one in color green. So you have Vm like so, and then you have V, and then dOm, and then ds, like so. So dOm ds. So let's compare now. You see that this quantity that I have here is the same as what I have here. Now this Vm that I have here is the same Vm that I have here. So for these two expressions to be equal, this quantity here, for these two expressions to be equal, this quantity here has to be equal to this quantity here. And so that is why I'm saying by identification, we see that V is equal to ds divided by dt. Is it clear now? That is why we have ds divided by dt, by just comparing the two formulas. C'est clair?
Yes.
Bien.
Yes, clear.
Bien. So this is, we've now talked about velocity. What about acceleration? Well, unlike velocity, acceleration has two components. It has one component along la normale. It also has another component along what? Along la tangente. Now let me just draw the trajectory one more time. Let's say the point M that we're talking about is here. Now the first thing that we want to draw is la trajectoire. Le sens. We have to indicate le sens du mouvement. It is in this direction. So let's draw a tangent to this curve here. If you want, you can draw a circle here and all that, but I'm going to skip all that. So if I draw like this, this is my tangent, and then this is so this is my tangent, the unit vector that is, So if I talk about the tangent, I'm talking about the unit vector. And then this is my composant normal. So unlike velocity, acceleration has a component along this and this. So if you remember your grade 12 physics, you're talking about things like centripetal acceleration. There's centripetal acceleration, then there's acceleration along this direction of velocity. So this one, you can think of it as the centripetal acceleration we were talking about. Okay, because we had a similar situation. You can think in those lines. So acceleration here has two components, along the tangent and along the la normale. Okay, so it means le vector accélération of the point M. So here sometimes you see gamma, in some books you see A. It's the same thing. A means acceleration. Sometimes you see gamma. Okay, so you can write whatever, you can understand that, okay, whatever I've written here is this. So accélération du point M par rapport à R. So this is going to be equal to, now it has a component along this tangent. So we can write it as this. So I'm just resolving the acceleration vector into its components. So here I have AN like so. Like so. So AM par rapport à R, and then AT, and then T, AN, T. Like so. Is it clear? Is it okay? If acceleration has a component along T, it also has a component along N. So a vector that has two components, this is how you can represent it. So this is the magnitude. This is the magnitude along the normal component. This is the magnitude along the component along the tangent. Hopefully you understand what I've written here. Now, by definition, what is acceleration? This definition for acceleration is true for any coordinate system, just like the one for velocity. We know that acceleration is defined as, the derivative. Acceleration is defined as the derivative of velocity. That's what acceleration is, par rapport au temps. Like so. That's what velocity is. Now, if you look at velocity, for la base de serré Frenet, what is the expression for velocity? Let me just go back, up, like so. For la base de serré Frenet, this is the expression we're going to use for acceleration, for velocity, sorry. So if I get this expression that I have here and inject it in this definition for acceleration, what am I going to have? I'm going to have V and T, like so. This is what acceleration is. Now here we have a product of two functions. So to be able to differentiate this, what do? We apply the product rule. So here I'll say apply product rule. Apply product rule. Like so. Apply product rule. So if you apply the product rule here, you have the derivative with respect to t of the vector v, and then we leave the second vector alone. And then plus, we leave the first vector alone, and then we say dt, and then with respect to time, like so. So this is what we're going to get. Okay? So this is what we're going to get. What we have here, we can understand. It is dv divided by dt, like so. But this one can be simplified a little bit further. So what is the expression for t, for this t? So you can clearly see that if you compare this expression that is here, this expression, and finally the final expression for v has to be in this form. We must have a component along t and a component along n. If you look at this formula here and what we have here, you can clearly see that we've gotten our component along t. However, we don't have a component along n. So we have to simplify this second part further. This part here carries a t. This also carries a t. So it simply shows that this at, the magnitude, has to be this quantity here. But here we are not seeing the n here. So we have to continue. We have to simplify further. So this is actually going to be equal to what? If we simplify further, this is going to be dv divided by dt, like so. T here plus. Let's replace the expression for t. Now, if you remember very well, the expression for t is dom with respect to ds. If you remember very well the expression, this is what we have. Okay, this is what we have. If you remember very well, this is what we have. Right, and then we also have the v, like so. So I've just replaced the expression. I've just replaced the expression for t. Well, actually here we have a simpler simplification. Sorry. What we can do is we have plus here. We have plus, and okay, let me just write it the way it is. We can actually, we have a simpler simplification than what I intended to do. So here I'm not seeing the n, right? Here I'm not seeing the n. Now let me just quickly scroll up like so and see the expression for n. Where is the expression for n? It is this expression. It is this expression. It is this expression for n. Now let's get this expression and write it. It is rho. We know that n is supposed to look like this. N is equal to rho, and then it is dt ds. It is dt ds. Let me just verify one more time. This is actually going to be simpler than what I wanted to do. Rho dt ds. Très bien. Rho dt ds. So this is what we have. Rho dt ds. Ah, look at what we have here. I want to see an n. This part is already there. The dt ds. It's already there. This is what I have here. The dt ds is already there. I'm only missing a rho. I'm only missing this rho here. So what I'm going to do is I'm going to multiply by rho and then divide by rho. You can see that I've done nothing here. I've not changed anything because this and this can simplify. Okay, this and this can simplify. So I've not changed anything. I've not done anything to this problem. Okay, I've just multiplied by rho and divided by what? Divided by rho. Is it clear? You understand what I've written here? Let me just go back to the expression for t. Okay, yeah, it's the same thing. Is it clear? I've just multiplied by rho and divided by rho. Is it clear? And actually, I'm missing one thing here. Am I missing anything? Am I missing anything? No, I'm not. I'm not missing anything. We leave the v alone. We differentiate the t. Let me check. It looks like I'm. Yes, the Violet, you have a question.
I have a question.
Yes, go ahead.
I have a question.
Yes, go ahead. Go ahead, ask your question. Go ahead, ask your question. Are you able to get me? I think there's a connection problem. Are you able to get what I'm saying?
Yes. How did it change from
Mhm.
dt over dt to dt over this?
Yeah, you are correct. That's where the mistake is. I was wondering. I thought I knew I missed something. I knew something is off.
Oh, you can get me?
No, I can get you. I think there's a disconnection. I knew I was missing something.
Hello?
Okay. I think there's
Yes, I can get you. Can you get me?
Yes, I'm able to get you. Sorry, connection problem one more time. So this is why online lessons are challenging. So there's always, we always have some connection problems. So are you able to get me now? Are you able to get Violet? The others are able to get me? So you just have to bear with me. The network is very, very bad. The network is very, very bad. Just exercise a little patience, so we'll be done in no time. So yes, Violet, you are right. I actually made the mistake. I made the mistake here. I forgot that there's a DT at the bottom here. So that's why something was missing in my formula. That's why something was missing in my formula. So what we can do here is we can say V, and then here we can say this dt that we have here. I can first of all say ds, and then I can say it is going to be ds divided by t, like so. So now it's correct. So now if you look at this, expression for n, because I want to see an n. I know that acceleration has a component along the tangent. It also has a component along the normal. I'm not seeing the n here, so I want to introduce the n. So to introduce the n, I need the dt divided by ds. I need the dt divided by ds, but how do I do that since I have a dt divided by dt? I'll use s. I'll write it the way I've written it, like so. Now this is fine. Oh, this ds divided by dt is equal to what? Let's go back. The ds divided by dt here, we say that by identification, the ds divided by dt is equal to v. We established this formula. So what I can say here, now that I've written whatever I've written, I can say that this is actually going to be equal to dv divided by dt, like so, and then plus v squared. And then here you have dt and then divided by ds. Now if you compare this expression that I've written here to this expression that is here, for me to have an n here, the only thing that is missing is this rho that I have there. That's the only thing that is missing. So to introduce this rho in this formula, I have to multiply by rho and then divide by rho. You can see that I've not changed anything. I've not changed anything. So here, this rho with this term is going to give me n. So finally, I'm going to get dv divided by dt and then t, like so, and then plus. Now this is going to give me n. So I'll have v squared divided by rho in the direction of n. So this actually means that the at in this formula here, this at here is actually going to be equal to dv divided by dt, and then an is going to be equal to v squared divided by rho. Is it clear now? C'est clair? Are we on the same page? Are we on the same page? Violet, is it clear?
So on the row, you just introduce it like that.
Yes.
With its inverse.
Yeah, with its inverse, so that I don't change anything, because I want to introduce the n. The only way I can introduce the n is I have the dt and the dt over ds, but then the rho is missing. So I multiply by rho and then divide by its inverse. And I multiply by rho and divide by rho to introduce it. Is it clear? Okay. The others, is it clear where the transformation I've made here and my conclusion? We've deduced the components of acceleration. The components are, we have the components dv divided by t for at, and then for an we have v squared divided by rho. Yes, Natasha?
So this squared,
Mm-hmm.
this squared because the ds and dt.
What?
The v squared, it's squared because this v here is equal to the ds over dt.
Yes, yes. Yes. So we have one v here, and then there's this what the other v is coming from this expression, from this ds divided by t. From what we established here, that v is equal to ds divided by dt. So we substituted here, we got a v. So v multiplied by v gave us v squared, and then divided by this rho, and then the n that we want to introduce. C'est clair? Okay. Right. So we've talked about acceleration and velocity. Let's talk about the radius of curvature. How can we calculate the radius of curvature? Now, before we calculate the radius of curvature, I want us to look at some quantity. Here. What do you think is going to be? Then what do you think is going to be if I take the vector product of acceleration and velocity? If I take the vector product of acceleration and velocity, let's see what is going to happen. Now you see that this is what is going to give us le rayon de the expression for le rayon de courbure. So if I take the vector product between acceleration and velocity, what am I going to have? If I take the vector product between acceleration and velocity, if I take the vector product, so let's look at what is the expression for acceleration. The expression for acceleration, I'm going to get this one here. This is the expression for acceleration. That is what I'm going to get. So here I'm going to have quoi? So it's going to be dv divided by t, and then you have a t here, and then plus v squared divided by rho, and then like this, and then vectorial the velocity, which is vt. So for the vector product, if the unit vector is the same, we know that here t vectorial t is going to be equal to 0. If it's the same vector and you take the vector product, it's going to be 0. But if it's the same vector and you take the scalar, if they are different vectors, you take the scalar product for these unit vectors, you get a 1. Okay. For the vector products, it's 0 if it's the same vector. So this vector, vectorial, this vector. Remember that the vector product can distribute itself, right? The vector product is distributive. If you look at the properties that we talked about the other time, the vector product is distributive. So what we have actually here is dv divided by t, and then t like so, and then vectorial, and then vt like so, and then plus v squared divided by rho, and then n, and then vectorial, and then vt. Because the vector product is distributive. Here we have the same vector t and t, like so. So this is going to be equal to 0. Remember the rules we talked about when I introduced the vector products. I told you about the rules. Hopefully you have not forgotten. So what we have here is v squared divided by rho, and then n, and then vectorial, and then vt, like so. This is what we have. Now here we can actually bien. So yeah, this is what we have. Okay, this is what we have. So here, this is a scalar. You can actually say it is v squared. You can write it as v squared divided by rho, and then multiplied by v, and then leave the vectors n and t in the product, in the vector product. You leave them in the vector product. Okay, so if you multiply here, you have v to the power 3 divided by rho. Now, what does this remind you of? Remember, there's a vector b. We know that b is actually equal to what? It's actually is t vectorial. B is t vectorial n. This is the expression for the other vector. Remember, there are 3 vectors in the basis. There's the vector t, the vector n, and the vector b. The vector b is t vectorial n. But here you can see that I've changed the positions of n and t. Oh, the vector product is anti-commutative. So if I change the positions of the vectors, then I'm going to have a minus sign. So here I'll have a minus sign like so, and then I'll put the vector b like so. Okay, I'll put the vector the vector b. Okay, this is what I'm going to have. So this is the vector product of acceleration and velocity. Now what happens if I take the absolute value on both sides? If I take la norme on both sides, I'm going to have la norme de. So we have this and then vectorial. I'm taking the magnitude, the magnitude on both sides. So if I take the magnitude here, the negative sign is going to disappear. So I'm going to have v to the power 3 and then rho, and then I'm going to have the magnitude of the vector b like so. Now b is a unit vector. The magnitude of a unit vector is always 1. The magnitude of a unit vector, so let me just say that b is a unit vector. The magnitude of a unit vector is 1. So here we see that we have v to the power 3 divided by rho, and then you have acceleration vectoriel la vitesse like so. So if you make rho the subject of the formula, you get that le rayon de courbure is given by v to the power 3 and then divided by the acceleration vectoriel the velocity like so. So this is the final answer. So remember this, you have to remember these formulas. To calculate le rayon de courbure, you use this formula. Le rayon de courbure, and then the acceleration has two components. The component along the tangent is this one. The component along the normal is this one. And then the velocity, the formula for the velocity. So these are the formulas that we have for this basis. C'est clear? What I've done, is it clear? Can we now move to le mouvement relatif? C'est clair? Right. Violet says it's okay. What about the others? What do you say? C'est clair? Natasha, is it clear? So for the last part, what I was saying is, for the last part here, we are finding we're looking at this quantity. We've taken the vector product between the acceleration and the velocity. So for the vector product here, we have this. I've put the formula for acceleration and the formula for velocity. Then here I said that the vector product is distributive. You can distribute it over a sum or over a difference. So when we distribute this vector product, we'll get what is on this line here. Okay. Then if you have the same unit vector t, u, and what, if you take the vector product, it is going to be 0 because it's the same vector. And then because we have the same unit vector. Okay. And then on the right hand, the only expression that is going to have a value that is non-zero, at least in this, I mean, the only component that we're going to extract is the other one, the one on the right. Now for here you can say this is a constant. V squared divided by rho is a constant. Even V is a constant. Okay, so you can factorize, you can take out these constants. You can multiply the constants alone and then leave the vectors in the vector product. So here we've multiplied the scalars, not the constants, but they're constants, but then we multiply the scalars. V squared divided by rho, V squared divided by rho and V, we multiply them, and then we just leave the vectors in the vector product. So V squared multiplied by V is V to the power 3 divided by rho, and then n vectorial t gives us the vector b, like so, gives us the vector b. So that is what we have. Okay, we get the vector b. So now we take the modulus to find the rho. We take the modulus. So if I take the modulus here, the negative on the other side is going to disappear because I'm taking the magnitude. I'm only interested in the magnitude of the quantity. So the magnitude of this product is the magnitude of the individual terms. So the magnitude of this constant and the magnitude of the vector b. The vector b is a unit vector. The magnitude of a unit vector is always 1. The magnitude of the unit vector is 1 because a unit vector is normalized. So it's like we divide the vector b by its when you divide the vector by its magnitude, you're sort of like normalizing that vector. So the magnitude is 1. So any unit vector is going to be of unit length. Okay. So here, that is why here the b disappeared, because its magnitude is 1. So we've taken the norm on all sides. Then we've made p the subject of the formula, and then this is what we have for the formula for le rayon de Courbillon. So this is what I said. Is it clear now?
Yes.
Okay. Brian, Michael, is it clear?
Yes, it's clear.
Okay. So let's now look at le mouvement relatif. After this, we'll now start solving serious exercises, because we now have a baggage. We now have a baggage that is sufficient for us to solve exercises on cinématique. The only thing after le mouvement relatif, the only thing that is going to remain is le changement de référentiel. Changement de référentiel, that is the only thing that is going to remain. However, after finishing today's lesson, you have all the necessary tools, all the requirements to be able to solve any kind of exercise. You have all the requirements to solve any kind of exercise on cinématique apart from le changement de référentiel. So after this, we'll start looking at serious exercises. So you have to make sure that you revise everything. You have to make sure that you revise everything. Now let's look at the last part for today. The last part for today. Now let me just what do I want to do? Let me just do this. Okay, up. Like so. So let's look at le changement de référentiel. Changement de... Oh non, le mouvement relatif. Le mouvement relatif, it is now where we're going to introduce le vitesse d'entraînement, vitesse de Coriolis, and all that. So we've talked about la base de serré Frenet. We've talked about that. Okay. Hop. Les mouvements relatifs. Très bien. Hop. Like so. Now, let me first of all draw some diagram here. Let's say we have a repère absolu. We have a reference frame. We have a reference frame. Let me maybe just do that. So let's say we have this reference frame in red. We have this reference frame in red. Like so. Then let's say we have another reference frame. We have another reference frame. We have another reference frame. Maybe like so. Like so. And like so. So we have this reference frame. We have two reference frames. We have this one. Then we have this one. We have this one in black. And then we have this one in red. We have this one in black. We have the one in black and the one in red. So let's say this is the y-axis, this is the x-axis, and then this is the z-axis. And then here, let's say that this is the y-prime axis, then this is the x-prime axis, and then this is the, maybe let me just, for consistency, let me just use the same color. Let me just use the same color for consistency. So this is the y-prime axis, this is the x-prime axis, and then this is the z-prime axis, like so. So let's say we have a point M that is moving, a point M that is moving in this black axis. So hence the black color that I've given to M. We have a point that is moving in this black axis. So what do you think is the position vector? What do you think is the position? Let's say this black axis has an origin O prime, and then the red axis has an origin O, like so. So what do you think is the position vector? The position vector of the vector from this origin to here. We have this line. Maybe I can do a better job here. So like so, draw a line. So from this point to this point, we have this. So let's talk about the position vector. The position vector of this point M, the position vector of this point M in this reference frame, X prime, Z prime, Y prime. The position vector of OM. Oh, here it's simple. So the position of M in this black reference frame is actually, the origin is O prime. So it is O prime M is going to be equal to, O prime M is going to be equal to, so the vector O prime M is going to be equal to X prime. It is going to be equal to X prime, which means it is somewhere on the x-axis. It has a certain location on the x-axis and a certain location on the y-axis. So it is X prime in the direction, I will say Ex prime, like so, and then plus Y prime, EY prime, EY prime, like so, and then it has a Z prime, and then EZ prime, like so. So this is how you can write the position vector. But then with respect to this, or with respect to this red axis, what do you think is the position vector of this point M that is here with reference to this red axis? Well, with reference to this red axis, it's actually easy again. You just have to look at the origin. So it is OM. So it is OM is equal to, so we are now here. So it is X, EX plus Y, EY plus Z, EZ. Now these two positions, these are positions, right? But then the position in black is known as, this position here is known as the relative position. The relative position. This is the relative position, and then the one in red is the absolute position. The absolute position. So absolute, this is the absolute position. This is the absolute position, then this is the relative position. So you can see that the movement of M in this reference frame X prime, Y prime, Z prime is relative. Then the movement of M in the red axis, or in the red reference frame, is X, Y, in the red reference frame is absolute. So this red axis here, this red reference frame, we can call it le repère absolu. So this is le repère absolu. So then the other one, we can call it le repère mobile. Repère mobile. So why is it mobile? Mobile, it can perform two types of movement. So this reference frame in black can perform two types of movements. It can perform translation. It can also rotate. So it can also perform what is known as rotation. So I'll give you an example of a rotation. I'll also give you an example of a translation later on. But then this is the position vector. The one in black is the relative position, and then the one in red is the absolute position. So we've defined our problem. Now let's talk about the velocity. What do you think is the velocity of the particle M in this black reference frame? Well, in this black reference frame, it's the same. I mean, it's not the same, sorry. We just have to take the derivative of this position vector, the relative position. So to find the relative velocity, we have to take to find the relative velocity, what do we have to do? We just have to differentiate this relative position. Okay, this relative position. But then let's look at how do we arrive at OM? How do I move from O going to M? From O to M? Well, I can move directly. But that's not the only path that I have. The other path that I have here to go from O to M is, first of all, going to O prime, from O to O prime, and then from O prime to M. That's another path I can follow. That's another path I can follow. I can follow, right? So instead of going directly from O to M, I can go from O to O prime, and then from O prime to M. Okay? So I can say the vector OM. So I can safely say the vector OM. I can safely say that the vector OM is going to be equal to O prime, like so, and then plus O prime what? O prime M, like so. I have the expression for O prime M. Now this is the absolute position. This is the absolute position. Because it's the position in the red reference frame. OM is the position in the red reference frame. So this is the absolute position. So with this, I can calculate what is known as the absolute velocity. With this, I can calculate what is known as the absolute velocity. The absolute velocity is the velocity in the red reference frame, which is fixed. Okay? The one that is not moving. The black one is moving. So absolute velocity is the velocity in the reference frame red that is not moving. Okay? So if I want to calculate the absolute velocity here, by definition, the velocity of the point M in the reference frame R. Now let's call this one, the reference frame in black, let's call it R prime, so that we can distinguish them a little bit better. Now let me see if... So are you following? Is everything okay? Okay. As expected. As expected, the connection. Right, so I got disconnected once more. So what was the last thing? What was the last thing I said? So let me just share my screen. What was the last thing I said? Are you able to follow? Were you following? What was the last thing I said? If you were able to follow. What was the last thing I said? The last thing I said?
You said if we want to express OM from the relative, relative what? Yes, from the first axis, you can go through O prime, then M.
Okay, right. So yeah, you can go from O to O prime, and then from O prime, then finally you arrive at M. However, this OM, this vector OM, is the absolute position because it is equal to this expression that we have here. This expression for OM gives us the same expression as the one we have for OM here in red. Okay, so it's still the absolute position. So if I differentiate this vector position, with respect to time, I'm going to get what is known as the absolute velocity. Hence here you see an A here. Okay, you're going to see an A here. Subscript A here. You see an A here to mean that this is the absolute velocity. So this is actually the derivative of the vector position, the absolute position OM with respect to time. If you want to get the relative velocity in this case is V with a small r here of the point M with respect to R, like so. It is actually the derivative of O prime M divided by dt. So this is known as the relative velocity. So this is the relative velocity. This is the relative, this is the absolute velocity. So this is the absolute velocity. This is the absolute velocity. Now let's find an expression. That is more expressive. This expression is not as expressive as the one we want to find. So let's continue developing this expression. So la vitesse absolue from m to r, like so, it is actually the derivative of OM with respect to t. Well, this is actually the derivative of O prime with respect to t. If I'm taking it from here, so plus the derivative of O prime m divided by dt. I've just expanded here. Hopefully you guys are able to follow. You call ends in under a minute. Okay, so what we're going to do is that we're going to exit the current meeting, and then wait for the new link so that we come and continue, because the meeting ends in less than a minute. So exit this one and then wait for the new link. Okay, so are you able to get me and are you able to see the screen so that we continue with our discussion? Ça va? Okay, can we continue? Can we continue now? Bien. So, like I was saying, I was talking about la vitesse absolue. I've managed to write it in this way. Okay, another connection problem. Let me just connect to the other network.